Well, there we go. Well, ladies and gentlemen, we now are talking about the periodic trends that we find on the periodic table. Let me get my pen going. Let's see. Let's go with blue. So, periodic trends. And what do we mean by that? That if you look at the periodic table, we're going to see several physical and chemical properties remain the same or consistently change in one direction or another. And so what we're going to do is take a look at these trends and do some definitions as well. So the first one is melting and boiling points. And melting point is defined as the range where the element becomes a liquid and no solid remains. And we say a range because some solids have a tendency to melt at, we can see a liquid at the same time we see a solid. And there's a little bit of a range. And sometimes this range is probably about 1 degree Celsius, or maybe half a degree, but that's what we call the melting point. And the boiling point is defined as the temperature where the vapor pressure equals 1 atmospheric pressure, or 1 atm. Now, when we're doing this, please take notes. I'll appreciate that. And you can always pause this and go back and relearn and write this down if you need to. So those are two definitions. And when we talk about trends, and there are certain trends we need to know. And for melting points for metals and nonmetals, and transition metals, it increases from the top to bottom. So as we go from the top and go down, the melting point increases. But for the first two columns on the left, it goes the other way. It decreases as you go top to bottom, or if you go from the bottom to the top, the melting point increases. And that's just the trends between the melting points. And there are a couple of exceptions. Metalloids, mercury, and magnesium are the exceptions. And when you go to college and learn more chemistry, we'll talk about why those are exceptions. For boiling points, there are no trends. Or if there is a trend, it is a bit more hard to explain. I'll leave that to college. All right, here's one, atomic radius. It is defined as the size of the atom calculated between determine the bond distance of two atoms bound together and then divided by 2. And the atoms have to be identical. So two hydrogens, here's the nucleus, is the other nucleus, and we measure the distance between the two. And I think this is about 53 picometers, where picometer is 1 times 10 to the minus 12 meters. So they're very, very small. And this is how we divide. And actually, I should say this is 106 picometers between the two. So divide that by 2, and then you get the distance between here and here is 53. Let me rephrase that. So that's what we look at the atomic radius, and there is definitely a trend with the atomic radius. Now, the size of the atoms, this is important, it's dependent upon the number of electrons and energy levels of those electrons. And there's something really freaky, interesting that goes on with the trends. So when you're looking at atomic size, and you gotta think of not just the size of the atom, how many electrons does it have, and the energy levels of those electrons, and where it is on the periodic table, because the actual trend is from the left to right, the size decreases. So it gets smaller as we go left to right. And if you go from top to the bottom, it's going to increase. Well, that makes sense. What doesn't make sense is this, going from left to right. Most people will say, no, that can't be right. But something that increases is what we call the effective nuclear charge. And that means the effective nuclear charge is the charge the outermost electron sees. I say sees, I'll put that in quotation marks, feels, there's another way, the attraction force, the force it's attracted, changes as you go left to right. And in fact, the force increases as you go left to right. And the reason why is the electrons partially shield the nucleus. So it's like having a book And the bigger the book, the more likely the electrons are being shielded. Now, the fact that electrons move around the atom, this is why we say partially, because electrons are always moving. So we have an electron out here. Here's my nucleus. We got electrons whizzing back and forth and going this way, and so we're going to have a partial shield, and it's all based on the electron energy. So if we go to the periodic table, as we go left to right, it's getting smaller, and that's because is that lithium is bigger than beryllium, and you got, if we got lithium, you get electrons out here. Beryllium it's got 2 electrons, but at the same energy. The electron cloud doesn't move that much, and beryllium actually brings them in closer because there's less shielding of the nucleus because of the electrons. These electrons are in the same place basically, so you get them pulled in. Goes up a little bit, and then it gets smaller and smaller and smaller. This is what I mean by periodic trends. The trends going left to right decreases for atoms' atomic size, but it increases as you go from top to bottom. And so that's what we mean. So let's talk about ions. And we'll do more theoretical stuff with ions later on in Chapter 4, but in this case we're looking at how ions are formed, and then basically when you add electrons or remove an electron. A cation, when electrons are removed from an atom, and they are positive because we've got more protons than electrons. And an anion, we've got more electrons than protons. Now, folks, the electrons is the one that moves. Protons don't. Neutrons don't. So basically, the protons and the electrons are the things that move, and this is what causes a reaction. And when we have a trend, the ion size decreases when we have cations. The more electrons we remove, the smaller the cation will be. So, Ca plus 1 is going to be bigger than Ca plus 2, and calcium is neutral is going to be bigger than Ca 1. So as we take more electrons away, the ion gets smaller. But if we go, say, oxygen, it's going to be smaller than O minus 1, which is going to be smaller than O minus 2. We're going to end up with more electron-electron repulsion and a decrease in nuclear charge, and the ion is going to get bigger and bigger and bigger, and that's going to be the trend. And so what does this mean? All these metals, everything, I'm going to draw this staircase. Everything to the left are metals, and then the ions are all positive, so they're going to be smaller than the atom. If we go to here, these are nonmetals. They usually will pick up electrons and get bigger as they form anions. These guys in the middle tend to be a little bit of both. And there's more complicated chemistry involved, but we'll get back to that later. All right, for the trend, for the family, that's the column. Top to bottom, it'll be increasing, but still smaller than the neutral atom. Going from top to bottom, the anion size is larger. From left to right, the metal will get smaller while the anions get larger. So cations, metal cations get smaller. Well, if we have an anion, they'll get larger. All right, so now we're going a little bit fast. If you need to pause, you can, and take notes. Ionization energy. It increases from going left to right. And we do see a little decrease when we go from the s to p orbitals, and we'll talk about more of those orbitals later. And it decreases as we're going down the column. If we want to remove large electrons, because like copper, you can remove 2 electrons or 1. Iron can remove up to 3 usually or more, and the ionization, you have to add more energy to get those other electrons away. For the periodic table, as we see, ionization energy will increase going from left to right. and it decreases. So increase, going left to right, and decrease, going from the top to bottom. And just think about the atomic size. These are getting bigger, so it's going to take less energy to remove an electron from francium than it will from lithium. And the ionization increases because as we go from left to right, the atom's getting smaller and it takes more energy to remove those electrons. Now, electron affinity is the amount of is the ability to attract an electron. So we have these ability to attract the electrons. The value becomes more negative, going from left to right. So when we mean by this, everything going from left to right, you're going to it'll rather attract an electron. Electrons, this is what E minus means, then these guys over here. Some of these can attract electrons and have done chemically, but not usually. That's probably 0.1%, and we'll talk about that in college. All right, shielding, we talked about shielding, a concept where the electrons are shielding or covering the nucleus from valence electrons. Those are reactive electrons, and that's what we mean by shielding. Some electrons partially shield and some totally shield, and we'll talk about there in chapter 4. Another one we're going to talk about, this is the last slide, is that electronegativity is the strength and attraction for an electron when two atoms are bounded together. And this is when we have two different atoms, like carbon and oxygen, or oxygen and hydrogen. And what happens is that oxygen has a higher electronegativity or higher pull on the electrons. It's like two kids pulling on a toy. If one's bigger than the other, the bigger kid's going to pull the toy closer to them. And this is what happens with electrons. So we're going to have more electrons around oxygen and hydrogen, and we'll end up with what we call partial charge. It increases from left to right, and decreases from top to bottom. Fluorine is the highest, then oxygen. Francium is the lowest. So we got this trend. And this is probably one of the most important trends that we look at. I always use this to figure out when I was working in research to figure out what's happening with my experiment. So electronegativity is a big one that you need to remember. All right, that's it, guys. Have a good day. Take notes, and see you in the next video.